Bismillahirrahmanirrahim. Hi everyone, I hope you are all doing well. I welcome you all to the class of real analysis. My name is Azmat Ali and I welcome you all at my channel Academy of Mathematical Sciences. Our discussion is continue on chapter number 3, Numerical Sequences and Series. The book that I am following here, this is the Principles of Mathematical Analysis by Walter Rudin. Lastly, we discussed Theorem 3.10. In today's lecture, I will discuss Theorem 3.11. This theorem consists on three parts, A, B and C. In this lecture, I will discuss the first two parts of this theorem, and the proof of this theorem is very simple and straightforward, but the theorem is very important. In the first part, we have to show in any metric space X, every convergent sequence is a Cauchy sequence. To understand this theorem, you have to just knowledge of what is convergent sequence and what is Cauchy sequence. So we have to show every convergent sequence is a Cauchy sequence. So firstly, I suppose a convergent sequence. Suppose that Pn is a convergent sequence in metric space X and converges to point P. Because it is a convergent, so therefore it has some limit. I say this limit is P. Then by definition of convergent sequence, for a given epsilon, positive real number epsilon, there exists a positive integer n such that the distance of this sequence from its limit will always less than some epsilon by 2. As epsilon is positive, then epsilon by 2 is also positive real number. This is the definition of convergent sequence. Whenever your suffix n is greater than or equal to this positive integer n. As Pn is a convergent sequence and this definition holds for every n which is greater than or equal to n. So if I take the suffix m, and m is also, and we take m is also greater than or equal to n, then this definition of convergent sequence also hold for Pm. So similarly we can write Pm, the distance of Pm from its limit P will always less than epsilon by 2. I have to show Pn is a convergent, Pn is a Cauchy sequence. So as you know, a sequence is called Cauchy sequence if the distance of any of its two terms is always less than some positive real number epsilon whenever your n and m are greater than or equal to some positive integer n. So by using triangle inequality, I consider the distance of Pn from Pm. So by just inserting the number P between these two numbers, we have the distance of Pn from P and from Pm to P. These both distances are less than epsilon by 2. So replace this by epsilon by 2 and replace also this epsilon by 2 whenever your m and n greater than or equal to positive integer n. This sum is equal to epsilon. So this shows that Pn is a Cauchy sequence. So this is very simple and easy. Next, it's in B parts, we have to show if X is a compact metric space and if Pn is a Cauchy sequence, then Pn converges to some point of X. In other words, in this theorem, we have to show in any compact metric space, every Cauchy sequence is a convergent sequence and converges to some point of X. Firstly, we define what is compact matrix. I have written a metric space in which every sequence contains a convergent subsequence and the limit of that sequence also belong to the same space is called compact metric. So compact metric is a metric in which every convergent sequence Every sequence contain a convergent subsequence, and the limit of that sequence also belong to the same space. For example, every closed and bounded interval in set of real number R, or you may take Rn. So every closed and bounded interval in R is always a compact metric space with respect to the usual metric. For example, if I take the interval 0 to 1, this interval, suppose I say this is I, then this I with the usual metric R, suppose usual metric is denoted by dr, then this I is a compact metric space, because if you take any sequence in this interval, then that sequence must have a convergent subsequence whose limit always belong to I. For example, if I take a sequence xn is equal to 1 over n, you can check that every term of this sequence belong to this interval. For example, if you put n is equal to 1, then your first term is x1 is equal to 1, your second term is 1 by 2, your third term is 1 by 3. All of these terms belong to this interval I. It means this sequence is defined on this interval I. Further, this sequence I always satisfied all the axioms of metric spaces, that is non-negativity, symmetric property, triangle inequality, etc. And further, every subsequence of this sequence always converges and its limit always belong to this. What is the limit of this sequence? This sequence has a limit as n approaches to infinity. This sequence has a limit 0, and 0 belong to this interval. Further, if you take any subsequence, suppose I take its subsequence xn plus 1 is equal to 1 over n plus 1. This is the subsequence of this sequence. If you find the limit of this sequence, the limit of this sequence is also 0 and belong to this interval. So I can say that every sequence defined on I has a convergent subsequence, and the limit of that subsequence always belong to this I. This shows that this interval I is a compact metric space with respect to the usual metric. What does mean by the usual metric? Usual metric mean the distance between any two elements is given by the absolute difference. So I hope now you have a clear understanding about what does mean by the compact metric. The main thing that you have to notice, in a compact metric, every sequence contains a convergent subsequence and whose limit also belong to the same space. So this is the definition that I will use in the proof of this theorem. This is the main thing that you have to notice here. Okay, so what we have to show? We have to show if X is a compact metric space, if Pn is a Cauchy sequence, then P is a converges. Pn converges to some point of X. Since it is given that X is a compact metric space, so by definition of compact metric space, every sequence in X has a convergent subsequence. Let P and K be a convergent subsequence and converges to some point P belong to this metric space X. We will show that your sequence Pn also converges to the same point P. It is given that Pn is a Cauchy sequence, so I will use the definition of Cauchy sequence. By definition of Cauchy sequence, for a given positive real number epsilon, there exists a positive integer n1 such that the distance between the two terms Pn and Pm, where the suffix m and n are greater than or equal to n1, this is always less than epsilon by 2. Say this is 1. This is the first definition that I have used for Cauchy sequence. Next, I use the same definition for the convergent subsequence. Since P and K is a convergent subsequence, as we have supposed, and it converges to P. So again, by using the definition of convergent subsequence, there exists a positive integer n2 such that the distance of these two terms will less than epsilon by 2 whenever your k is greater than or equal to n2. What I have to show? I have to show that Pn converges to Pn converges to P. This is my target. So to show this, I will use triangle inequality. This is my triangle inequality, and you can see here I am involving this term P and K. So this triangle inequality will hold when these two suffix n and nk both are greater than or equal to positive integer n1. So I am writing here after this. Choose k. What is k? K is a suffix which is greater than or equal to n2, for which this definition hold. Choose k large enough so that your nk is greater than or equal to n1. Now let n is greater than or equal to n1, and using the triangle inequality, this is the triangle inequality that I am using for these two numbers Pn and P. This is less than or equal to Pn k, and this is the distance of Pn k to P. As n and nk both are greater than or equal to n1, so this distance is less than epsilon by 2. How this is less than epsilon by 2? By the definition of Cauchy sequence. As Pn is a Cauchy sequence. As Pn is a Cauchy sequence, that's why the distance of any two terms whose suffix is greater than or equal to n1 is always less than epsilon by 2. So if I take one term is Pn and other is Pnk, and I say both of the suffix n and nk are greater than or equal to n1, it means this definition holds also for these two terms. So it means this definition also hold for Pn and Pnk. And this is clear from 2 because Pnk converges to P as a convergent subsequence. So replacing this term by epsilon by 2, and this is also epsilon by 2. So using 2 and 4 in 3, this gives distance of Pn from P is less than epsilon by adding epsilon by 2, epsilon by 2. And this shows Pn converges to P. Hence, every Cauchy sequence in a compact metric space converges to a point of X. Pn was originally a Cauchy sequence. Now it is a convergent sequence that is required. Hence, every Cauchy sequence in a compact metric space converges to a point of X. In the third part of this theorem, we will show that every sequence in Rn is a convergent sequence. That I will discuss inshallah in the next lecture. I hope now you have a clear understanding about these two parts of this theorem. These parts are very important. If you find this video helpful, please like, share and subscribe my channel. See you in the next lecture. Take care. Allah Hafiz.